Hello, this video is in continuation with the classification of the organometallic compound. I had already discussed the main group elements classification, and now I am going to discuss the classification of organometallic compounds of the transition metals. Transition metals form metal-carbon sigma bond with organic groups. The sigma bonded organometallics of transition metal are generally less stable than those of the main group elements. The reason for the instability of a large number of binary transition metal alkyls or the aryls appear to arise from the coordinatively unsaturated character of the metals. So the term coordinatively unsaturation . So this coordinatively unsaturation, when you will be counting the 18 electron rule of the valence electron of the compound or EAN, so if it is not obeying the 18 electron or the EAN effective atomic number rule of Sizwick, so those are called as coordinatively unsaturated, and due to this, these compounds leading to easy pathway for thermodynamically possible decomposition, and that, in another word, you can say that it will be unstable. Some of the organo transition metal having metal carbon sigma bond and that are found to be very much stable and like tungsten CH3 whole 6, then CS3 MnCO5, then you are having pi C6 H6 Fe, then CS3 CO. These are the few examples in which it has been found that the metal is forming sigma bond and are a stable one. This has been pointed out that the stability also depends on the presence of other your ligand which are pi bonding ligands, like the presence of CO, which is pi bonding ligands. In this case also the CO is present, which make this transition metal alkyl or the aryl compound stable. Thus the presence of this pi bonding ligands of the organometallic compound of the transition elements increases the stability of metal carbon your sigma bond, and thus makes the compound stable. Another reason of your instability with this transition metal, if the alkyl group is having also beta carbon atom, and beta carbon atom, if that will be having hydrogen atom, then it will be unstable. Suppose we are having a compound like your tungsten with this ethyl. So this tungsten with this ethyl, since this ethyl group is having beta carbon atom, and the beta carbon atom is having also the hydrogen one, so what happens, this is having the other ligands too, this is having other ligands too, so this will dissociate to metal hydride, and there will be formation of alkene. So this is called beta elimination reaction. This is called beta elimination reaction. So this can be managed, and this can be made your stable if you remove this hydrogen at the beta carbon, then the compound will be stable. Another thing is that if the other ligands which are attached is also having the pi acceptor, that means the pi bonding ligands are present, then also this will be stable. But the beta carbon having the hydrogen can be replaced with the help of, suppose, trialkyl phosphine or trialkyl arsine or any halide, or your RO group, if you replace it like that. This also can be done if you do like this. The CS2, the first is the replacement of the hydrogen of the hydrogen available at the beta carbon of this alkyl chain, and another is if you replace the beta carbon with this phenyl group. So there is no beta carbon hydrogen present, so this will be stable. So transition metal form a stable organo-transition metal compound with also the alkenes, then alkynes and some other carbon containing compound having electrons in their pi molecular orbital, and with the vacant orbital of the transition metal give rise to an arrangement in which the metal atom gets bound to all the carbon atoms over which the pi molecular orbital of the organic ligand is spread, which I discussed in the first video. The ferrocene, all the pi molecular orbital is attached, which is the part of the carbon chain, and those are attached with the metal. So this your transition element, so it forms with just now we said it is also forming with alkene, also it is forming with your alkyne. So such type of complex we will go through when we will be going ahead with the transition metal the organometallic compounds of the transition metals. So let us have some example of the transition metal. This is the platinum complex. This platinum complex is known as the J salt, which is the first your platinum olefin complex in 1827. It was synthesized by Jess, and that's why it is named as J salt. So the ferrocene I had already discussed. This is Schwarz reagent, which is having zirconium, and then Cp I had already discussed, and it is also having hydride and this chloride. This is chloro, then bis cyclopentadienyl, hydrido, then your zirconium. Then Wilkinson's catalyst I had already discussed. The Coleman's reagent I had already discussed. Now we will go for the another type of classification, that is the organometallic compound of carbene and carbine. So this carbene and carbine is nothing, it is metal alkylidine. When the carbene is present, this is Cr2, so this will be not only double bond, and in the case of your carbine it is having triple bond. So it is having your double bond due to the back bonding also. This is also having some back bonding, so that will be discussed later on. But here I want to discuss this Fishers and Strauch's your carbene and carbine. The Fisher carbene is the carbon is singulate. The carbon is singulate. You know the spin multiplicity calculation, in which your formula is 2s plus 1. So in the Fisher, what happens? In the Fisher, what happens? This both the electrons are in the sp2 hybridized orbital, and it is paired, and so the the total spin of the electrons available is 0. So 2 into 0 plus 1, so it is 1. So this carbon in the case of Fisher's carbene is singulate, whereas in the Strauch's it is triplet, and that will be discussed when we will be going for the carbene and carbine complexes of transition metals and also the main group elements. So here in this case of carbine, the Fisher's carbine, you are having this carbon is having 3 electrons, so it is doublet. doublet in the sense, as I discussed earlier, in the case of carbene, the two electrons in the hybrid orbitals and it is paired, so there is only one electron which is having your spin, that is half plus 1, so it is 2, so it is having a doublet character. And in this Strock's carbine, it is having your what? Quartet type of nature. So such compounds are formed also by the main group elements as well as the transition elements, and these are further classified, as I said, the Fischer's carbene and carbine, and also Strock's carbene and carbine, on the basis of the spin multiplicity and spin multiplicity, especially the electrons available on the carbon. So the examples here of the carbene and carbine organometallics are for the main group, you are having PH3, then P double bond CH2. This is a very famous compound which is called Wittig reagent. This is your triphenyl phosphonium halide, and there is another which is also in the case of your sulfur, the triple bond character, which is having CF3, then triple bond SF3. It is your 2,2,2 trifluoroethylidine what? Sulfurane, because the it is a polyvalent type of sulfur, that's why it is called as sulfurane. So the from the your main group, now you move to the transition. Then there is a example of this compound H, then C, Me3, then you are having Me3, C, CH2, Me3, C, CH2, Me3, C, CH2. This is your neopentyl. So 1, 2, 3 tris neopentyl, your neopentylidino tantalum, and similarly tungsten forms this type of having the carbonyl group, 4 carbonyl group, and 1 is the iodine. So this is tetracarbonyl iodo, then phenyl methine tungsten, which is having the carbine type of triple bond, and this is all about the classification of the organometallic compound.